G'day viewers. In this segment I'll tell you about explicit congestion notification. So our topic is how routers can help hosts to avoid congestion. We've talked about the network layer needing to work together with the transport layer to avoid congestion and come up with a reasonable bandwidth allocation. So far routers have been helping by, well, dropping packets, which is not very helpful. It's some kind of signal, but it's a little bit implicit. With explicit congestion notification, routers are going to send an explicit signal to hosts saying that there is congestion. And this is a kind of congestion control or a form of support for avoiding congestion, which is being rolled out, deployed in the internet today. So mostly this is a mechanism that's not used yet, even though it's been around for a long time. And its time is coming as it's deployed more and more. So to understand why explicit congestion notification is useful, let's consider the difference between congestion avoidance and congestion control. If you think about it, with classic TCP, actually it's not avoiding congestion. The way it finds out where to set the congestion window is TCP really, by increasing the congestion window, drives the network into congestion. Then it does a pretty good job of recovering. So TCP is actually causing congestion. And it has to do this because it needs to seek some kind of loss, which only comes through congestion, to know when to slow down. Okay, I mean, it works pretty well, but you know, if you want to build a good network with low delay and low loss and whatever, wouldn't it be better to actually avoid congestion? This is what we would like to do. We would get better performance, low levels of loss, lower levels of delay, you know, while still getting the high throughput. We just need to find a way to do this. This is the real question. How can we do this? With classic TCP and routers providing packet loss signals, we really couldn't do this very well. Well, maybe there are options. With explicit congestion notification, we're going to build supporting to routers to help us avoid congestion. And this will get us to a better place. This is something that's going on in the internet. So to just understand a little bit about how routers could help, I want to remind you of this slide from the beginning, almost, of when we talked about congestion. We talked about the network providing feedback via a signal, and there were several different kinds of signals shown here in this column. The first one was packet loss. This is what classic TCP used, and many forms of TCP use today. Well, most forms of TCP interpret packet loss as congestion. We said this is a good mechanism in that it's hard to get wrong. You can't build routers that don't drop packets when congestion is occurring. But the downside that I'm talking about now is you hear about congestion late, after it's already occurred and done the damage. Well, there are two other signals that we can use instead. Packet delay, because delays will begin to go up as soon as congestion is approaching, and router indications or explicit notifications of some kind from routers telling you that there is congestion occurring. The big benefits of these two approaches are that we hear about congestion early. And they're a little different in some ways. Packet delay is a bit of a signal that can fluctuate, so we need to work on how to infer congestion from it. And exactly how to do this is not so clear. I'm not going to talk about this, although if you're interested, there are various kinds of congestion control around that do use packet delay. Instead, what I'll talk about is a simpler and cleaner mechanism whereby we use router indications, messages from routers that congestion is coming. The downside here is simply that we need router support, which is why it's taken so long to deploy. But once it is deployed, we'll have a fairly clean way of recognizing when we're driving the network into congestion. So this mechanism whereby routers provide congestion indications is called explicit congestion notification, or ECN. The idea is, it's fairly straightforward. The idea is that the router is going to detect the onset of congestion by monitoring its queue. Instantaneous queue size can fluctuate a lot, just like our RTT data could fluctuate a lot. So the router can use some kind of moving average over it to get an estimate of the average queuing time. That should be near zero. If that begins to go up, it means that a persistent queue is beginning to build and we might be getting near congestion. When this happens, the router here will know that we're near the point of congestion, and it will then mark the packets that are going through it which are experiencing congestion. Marking is simply turning a bit on the IP header. So it's just flipping a bit is marking it. Now there were some bits in the IP header, if you go back and look at them, which are used to do this, the ECN bits. Now, when a host receives this packet, when it goes through the network and arrives at the host will know that it has been marked, and it will know that that packet experienced congestion. What the receiver will do is it will say, well, this congestion, I need to tell the sender about it, because congestion, previously we detected it with a packet loss. Here marked will be considered to be the equivalent of having lost a packet. It's just we're hearing about it ahead of time. What the receiver will do then is that it will send this congestion signal back to the sender. Now, actually the congestion notification is carried on the IP layers because it has to be done in the network, so it's a network layer protocol. When the mark arrives at the receiver, this information is passed up to the TCP layer, because it's the TCP layer, the transport, which will need to respond to congestion and interpret these marks and do something about it. So at the TCP level, in packets that are going in the other direction, ACKs and so forth, we will send this congestion signal back to the sender. And the sender here, I'm just going to write sender and receiver. The sender here will get that congestion notification. If there'd been an actual loss, it would have worked out from the ACK stream that there was a loss. Instead, there's another side channel whereby it gets these congestion notifications. But it treats them as equivalent as a loss in that it will half its congestion window and do all of the slowing down and so forth. So TCP really doesn't need to do anything new with explicit congestion indications. It just needs to treat them as loss. And with that, we're pretty much done with ECN. The advantages of ECN are that routers are able to deliver a clear signal to hosts of congestion. The congestion is detected early. This means the sender can react to it before it causes loss and excessive delay. So we're getting a better quality of network service by avoiding this congestion. And you might have wondered about whether, why these bits were flipped on packets as they went through, and congestion notifications were carried, congestion signals were carried from the receiver back to the sender. But what we've done here that's kind of clever is we've sent these congestion indications while sending no additional packets in the network. When the network's getting congested, it's not generally a good time to be having routers generate extra packets, which are another source of traffic. So we're simply using bits on existing packets so we don't amplify the traffic. The disadvantage of all of this is really the deployment question. That we need to upgrade the routers to produce these indications and the hosts to make use of it so that TCP will operate a little differently. It's not until you've got them both upgraded that ECN will be deployed and used on the internet. And it's a little bit of a chicken and egg situation, since you could wonder whether to upgrade the routers if the hosts haven't been upgraded, or the hosts if the routers haven't been upgraded. But we're getting there, and in the future you can expect that TCP-style congestion control will use explicit congestion notification from routers, as well as selective acknowledgements. And that will make it just that little bit better than most of the versions of TCP congestion control that we've seen. And now you know how congestion control works.